All right, you ready for the next step? So the next step in what we're learning about in Module 5 is we've learned about random variables, and we've learned that a variable can be a symbolic representation of an outcome from an event. And we're going to have some random amount when we have an event. And that random amount could be like heads or tails, where our variable has 0 represent like tails and 1 represent heads. Or our variable is like what's the number on a dice when we roll that single die, and randomly we'll get 1, 2, 3, 4, 5, or 6, and so the variable is going to represent the outcome of the event of rolling the die, and we'll have variables represent outcomes, and those variables can be discrete or they can be continuous, and if they're discrete they could be finite or they could be infinite. So again, learning vocabulary, laying the foundations for the field of statistics. That's kind of what we're doing here. We're learning to speak the language of statisticians. And that can be a little laborious sometimes. You're like, wait, how do you say sprinkled donut in French? Like, you got to learn the syntax, man. You got to learn the vocabulary. So that's what we're doing here. And now the next thing we're going to learn is discrete probability distributions. And so the probability distribution for a variable describes how probabilities are distributed over the values of the random variable. And so we saw that when we looked at slide 17. And we saw here that the variable is 0, 1, 2, 3, 4, or 5, representing how many cars are sold in a single day. And then here's like the probability distribution. It's a tabular, meaning it's a table. It's tabular. It's a tabular representation of the variable x, which represents the outcome of the event that we're measuring, how many cars were sold on a day, and that could be 0, 1, 2, 3, 4, 5, or 5. There are those 6 possible outcomes that the variable could be, and here are the associated probabilities of realizing one of those outcomes in a table, and so we call this a tabular format. And so we come back up here to this definition, discrete probability distributions. The probability distribution, right? It's the distribution of probability for a random variable describes how probabilities are distributed over the values of the random variable. So the values of the random variable are 0 through 5, and here is how those probabilities are distributed. And we can represent that in a tabular format, and we could also represent that in a graphical format. And so here's what that would look like in a graphical format. Number of automobiles sold during a day, and then here's the probability of that occurring. And so that is, the discrete probability distribution. It's a probability distribution. It's a distribution of the probability. And we can describe a discrete probability distribution with a table, graph, or formula. And so here, there are 2 types of discrete probability distribution. So we're going to learn a little bit more about probability distribution, and in particular, discrete probability distribution. What does discrete mean? Remember, when we have a variable, it could be discrete or it could be continuous. And discrete means we're dealing with whole numbers, right? Like, it's not fractions of a person, it's not fractions of a car. That's discrete. Continuous would be the fractions. It's like height, weight, speed, distance. That's continuous. Discrete is a whole number. And so we're dealing with discrete probability distributions. It's the distribution of probability over all the values that the variable can represent. And so 2 types of discrete probability distributions. The first type uses the rules of assigning probabilities to experimental outcomes to determine probabilities for each value of the random variable, right? So we're going to use rules, right? Whatever the rules are for assigning probabilities to experimental outcomes. And how do we assign probabilities to different outcomes? We could do that with the classical method. We could say, hey, all the probabilities are equally likely. And so that would be like rolling a fair die or tossing a fair coin. The probabilities are equally likely, right? That's the classical method. We could do the relative frequency or the empirical method, where we gather some data through a large number of observations. The law of large numbers will then show us that this is what you get if you do this thousands and thousands of times. And this is kind of how machine learning works, actually. It's like this brute force, try and try again until you get a better and better outcome. It's a kind of a little bit of an interesting application of the law of large numbers. And you could also determine probabilities through subjective experience. And you could just say, it's my opinion, this is what it's going to be, and I've been doing this for this long, and and that's the probability. So use the rules that we've come across, the different methods of assigning probabilities to different outcomes, right, to determine the probabilities for each value of a variable. And then the second way we could do it is use special mathematical formulas to compute the probabilities for each value of the random variable. And that's where we start to see this idea of having like an fx, right, where fx represents a function. There'll be some function or formula, and you could really pretty much use those terms interchangeably in the way we're talking about them. So there'll be some function or formula, and that function or formula will produce some result, some probability that we could use for the different outcomes that a variable is storing. Depending upon the outcome the variable stores, it will produce some probability of that occurring. And so those are the ways that we could determine the probabilities for different outcomes, right? For each value of the random variable. So discrete probability distributions, when we are looking at probability, of course, probability is measured on a scale from 0 to 1. 0, it's not going to occur. 1, it definitely will occur. And then all of the different continuous, possibilities between 0 and 1. So, fractions of fractions of fractions and decimal points, right? All the way from 0 to 1. So that's how we measure probability from 0 to 1. And the probability distribution is defined by a probability function. So the distribution of probability is going to be defined by some function or formula. So even when we get all of it through these methods here, there's going to be some formula some mathematical representation of what is occurring. It's going to be some formula that will represent the probability of, different outcomes, right? So based upon different outcomes, we'll have different possibilities. So if our outcome is 3 cars in a day, the probability of that is 0.14. If our outcome is 5 cars in a day, the probability of that is 0.01, low probability. 1 car a day, that's the highest probability of 0.39. And then all those probabilities there have to add up to 1, because not pretty much, no pretty much at all involved in that, but this is right here our sample space, right? It's our sample space. These are all the sample points, all the possible outcomes that can occur. And so we look each day to see what is the outcome, and the probability of that certain outcome is listed over there based upon empirical data in this case. So when you look at this slide here, right, where it has this information, it says the probability distribution is defined. The distribution is defined by some probability function denoted by fx, and that provides the probability for each value of the random variable. Right, so for each value of the random variable, 1, 2, 3, 0, 1, 2, 3, 4, 5, this function will produce or define the probability for that value of the random variable, right? And so coming back up to this, jumping around, the probability distribution is defined by a probability function denoted by fx. So fx is, very common notation for a function that provides the probability for each value of the random variable. So it provides the probability for each value of the random variable. I'm just going to bold that and italicize it. The required conditions for a discrete probability function are for any value of x, that has to be greater than or equal to 0, right? When you put any value of x in there, the probability that comes out. So this is a function. X is like the random variable we put in there. And we put something in there, any value of x, the probability that gets produced has to be greater than or equal to 0. And then the sum of all the probabilities for all of the possibilities that x can be has to be equal to 1. And that's what you see here. The sum of all these probabilities for any of the 6 values of x that we enter into this function, the sum of all those probabilities has to add up to 1. And that's just the definition of probability, right? When we're looking at all of the possible sample points, all of the possible outcomes in a sample space, all of those possible outcomes, all of those possible sample points, they have to add up to 1. That's just like the definition of how, like if this is the event space, the sample space of all the different outcomes, all of the different things that can occur, right? The probability of them occurring, right? This has this much of occurring, this much of occurring, this much occurring. All that has to add up to 1. That's just reductionistic logic. Discrete probability distributions. There are three methods for assigning probabilities to random variables. We already saw this. I don't know why they listed it again. The use of the relative frequency method to develop discrete probability distributions leads to what is called an empirical discrete distribution, right? So if you use this method, it leads to empirical discrete distribution. So we're talking about discrete probability distributions here, and if you use empirical, statisticians talk about as empirical discrete probability distributions, right? I would throw a probability in here, right, just to clarify, and I'll put that in parentheses because the textbook didn't have that, but it leads to empirical discrete probability distributions. I'll leave the parentheses out. We're just going to rename it. I think it's more clear. All right, so here's an example of DiCarlo motors, and this is the one that we see in slide 17, but kind of we're going to build up to that. And so slide 17 was this deal here, right? And we're on slide 11, so that's that deal. And then here we come back to slide 11. So we have the number of cards sold, 0 through 5, and the number of days that this occurred. So on 54 days out of 300 days, we sold 0 cars, or DiCarlo Motors did. On 117 days out of 300 days, 117 out of 300, we sold 1 car. And so with our random variable, our variable here, if our x is the number of cars sold in a day, you can see we're just assigning our variable. This looks totally redundant to me. Like, what's the point? But again, we're creating a framework for kind of thinking about things, that when we understand this framework of having a function and having a variable represent some outcome from an event or an experiment, right, we are going to be able to put in that variable, and then it'll produce the probability. And then we're going to see other functions, other formulas that are more complicated for, you know, putting a value in. And those are going to be like Poisson. I guess it's up here. You know, I thought we had a slide that really kind of showed it, and I'm not sure where that slide went. Oh, here it is. Binomial, Poisson, hypergeometric. That's kind of a cool name. But that was ahead of us. That's why we haven't seen that. So yeah, so that's the idea of having this framework and having variables and having functions. So using past data is empirical. It happened in the past. On daily car sales for 300 days, a tabular representation of the probability distribution for sales was developed. So here's that tabular representation. And with this tabular representation, we could say, what's 117 divided by 300? So I could go here, and I could do calculator, and I could do 117 divided by 300, and I get 0.39. And there's 0.39 there, right? Or I could do 72 divided by 300, so I'm going to clear this. I don't know which one I push. I really don't know the difference between that. That's totally funny. And I could do 72 divided by 300, and I get 0.24, right? So this is how I'm calculating the probability of those numbers there. So that's, then we could do a little graphical representation. So there's the graphical representation. And in addition to tables and graphs, a formula that gives the probability function fx for every value of x is often used to describe the probability distributions. So here, I'm starting to highlight formula in orange. We're going to see formula there. We're going to see formula here. And these are some of those formulas. We were just looking at the discrete probability distribution. And here we have discrete uniform distribution, which we're going to learn about in the next one. And we also learned about previously, we learned about empirical discrete, right? So empirical discrete probability distribution was for this one. And we'll put uniform, right? We'll also put uniform right here, because classical is going to be the uniform one right here. I don't know why they didn't call it discrete classical probability distribution. I guess they just wanted to confuse us a little bit. But you got to kind of think it through and kind of put all the pieces together. And that's what I don't care for about statistics. It could be more clear. So in addition to tables and graphs, we were on this slide here. And now we're on this one. Yeah. A formula that gives the probability function fx for every value of x is often used to describe the probability distributions. So a formula, right, that gives the probability function, fx. So formula and function, I don't know. That feels like a little convoluted, like they're using extra words when they don't need to. But we'll have some formula or function, fx, that for every value of x, right, describes the probability distribution. So it's a formula or a function, right? And you can just see this right here. There's the function. And that function for every value of x that's possible, and when it's discrete and finite, right, it'll be like a limited number of whole numbers. When it's discrete and infinite, it'll be unlimited amount of whole numbers. It could be, you know, any amount of whole numbers. And if you're like, what's a whole number? We can come over here and whole number defined. And a whole number is a number without fractions or an integer. And I'm going to do real number. What's a real number? In mathematics, a real number is a number that can be used to measure a continuous one-dimensional quantity. So that's a real number versus a whole number. And I think what's an integer? I'm trying to remember what's the one that's like 0 or more. That's what I'm trying to remember. An integer is a number that is not a fraction, a whole number, a thing complete in itself. What is the phrase for describing a number that is 0 or more and is also a whole number? The phrase you're talking, non-negative integer, non-negative integer. I thought there was like I thought there was a phrase for numbers that are 0 or greater. Is there something like that? Maybe it includes fractions also? I don't know. But non-negative, the phrase you're thinking of is non-negative number. Yes, a non-negative number, a non-negative integer. And I did define integer up here, but I guess an integer could be positive. I don't know. I still think maybe there's some phrase out there. I just can't think of it. So some of the discrete probability distributions specified by formulas are the discrete uniform distribution, binomial distribution, Poisson distribution, and hypergeometric distribution. So these, I put them also in orange. Right? I'm using bright orange just to illustrate that we're learning and using formula, this word formula and function here. And I put these in a light orange to show that these are some of those formulas or functions. And a discrete uniform, right, is going to be this classical one where all of them are equal. And so here's the discrete uniform. A discrete uniform probability distribution is the simplest example of a discrete probability distribution given by a formula. I don't know, man. They said discrete, like convoluted, right? Statistics is convoluted, the way they talk about stuff. But discrete uniform probability distribution, and then over here they were calling it discrete. I'm going to take out this dash and call it discrete probability uniform distribution, since that's what they call it on the next slide. I don't know why they're trying to confuse us, but discrete probability uniform distribution, discrete uniform probability distribution, that's what I want. Discrete uniform probability distribution. And so here's discrete uniform probability distribution. The simplest example of a discrete probability distribution given by a formula, right? And so discrete uniform probability function is fx is equal to 1 over n, where n is the number of values of a random variable may assume. The values of the random variable are all equally likely. And so that would be like, you know, flipping a coin. So it's 1 over 2. There's 2 values the random variable can assume. Or rolling a 6-sided die. It's going to be 1 over 6. And so there's 6 values the variable may assume. So that's like the simplest of a function. And then whatever the variable is, you would, you know, put this in here and you'd get, you know, 1 over 6 every time. Because that's the probability when you roll 3. What's the probability of 3? Put 3 into this, and your result is 1 over 6. Put a 2 into this, your result is 1 over 2. But the idea is that there is some formula or function that could describe what you discover, and you could create that. And there's already some formulas and functions to describe different situations. So we're going to learn about different situations and formulas and functions that apply to them. But that's the general idea. In the next video, we're just going to have ChatGPT take a swing at describing to us what we just went through, discrete probability distributions, and see how ChatGPT describes it. And then we're going to ask ChatGPT to do a couple of quiz questions and examples for us and work through them just to reinforce it, and then we'll move forward. But that's the game plan. See you in the next video. It's 10:59. It's 10:59. It's right before 11. That's a good stopping point, you know, for this video. We'll record more in the next video when it's 11.